I'm delighted to welcome you this evening to tonight's event in our Thought Leadership Series, Digital Design of Retaining Walls. My name is Catherine Barwick. I'm a Client Manager with Engineers Australia. In keeping with our tradition, I'd like to acknowledge the traditional owners of the land. There we go. And pay our respects to elders past, present and emerging. Tonight's event is being hosted with our industry partner, Austral Masonry. Austral Masonry is one of Australia's largest manufacturers of concrete masonry blocks, retaining walls, pavers and stone products. Austral's innovative solutions can be seen on their high-end architectural projects and landscaping designs. Their commercial solutions include large-scale segmental block retaining wall products and permeable segmental block paving. Austral takes pride in its products, which are of the highest quality and both durable and beautiful. Tonight we'll hear from two speakers, followed by audience Q&A panel discussion. Can I ask that you please make sure all your phones are off? Tonight our first speaker is Chris Lyons, Associate Geotechnical Engineer with Arup. Chris has 20 years experience covering geotechnical design of various types of deep and shallow foundations, ground improvement, retaining walls and slope stabilisation works for both static and seismic loadings. His recent project works include proof engineering for multiple reinforced earth walls up to 15 metres high, design of 23 metre deep fill embankments, and he is currently working on the design of deep station boxes, ground movement prediction and damage assessments for the Melbourne Metro project. Chris has been involved in all stages of project works, from investigations and detailed designs through to construction inspections and high-level project coordination. He brings a combination of strong technical skills, clear communication and on-site construction experience to all of his projects. Chris has several years of international experience, including working in the UK, New Zealand and the Gulf regions. Without further ado, please join me in welcoming Chris.
Good evening. Can you hear me without the microphone? Is that okay? You're important, so that's good. So thank you very much for that introduction, Catherine, and thank you very much to Engineers Australia for the support of this event. Thanks also to the Austral team as well, and Michael. Thanks for your support to the industry. It's always a pleasure to work with you, and it's great being here down at the Brickworks studio, so fantastic. So my presentation tonight is the digital design of retaining walls. So as Catherine's said, I'm a geotechnical engineer. I'm not a digital programmer, I'm not into digital analytics. I'm a geotechnical designer that's been doing design of retaining walls for 20 years, a bit over. I've started off with hand calculations, moved on to software. I think I used Plaxis when it was a DOS-based version, which I expect many of the young people in this room don't even know what DOS-based is these days. But then progressed through the design of projects, the coordination of projects, and more into a digital environment, implementing digital technologies on the delivery of projects, as well as looking at strategies within Arup nationally and also talking globally about bringing more digital design into our work. So my presentation tonight's got 4 topics. So the first part is conventional retaining wall design, the simple things we have to do no matter what we're doing for retaining wall design. Then having a look at the state of play in terms of a digital age and how that influences our design. And then moving into some of the things which are developing in the industry, so automation, parametric design. And at the end, a bit of a review, so a bit of a summary of my perceptions of digital design of retaining walls and what are the key things to take away. So, conventional retaining wall design. So these are things that we have to complete to make a successful retaining wall design, no matter what we're doing, no matter what software, no matter how complex we're getting, whether it's just a hand calculation. So we have to understand the design layout and objectives. What are our profiles like? Are we designing it for a road? Are we trying to control ground movements? Is it a strength case? So what are we trying to achieve with our retaining wall design? The next is the geotechnical model. So geological model, understanding groundwater, understanding how the ground's likely to behave, and then also geohazards, which may challenge or be issues for our retaining wall design. Thinking about the design scenarios, what are our loading cases? Is it static or seismic loading? What are our durability requirements? What's our design life? What are the things that are going to drive our design? What codes do we have to adhere to? And then it's the geotechnical design parameters. So what are the actual values that we're going to use to calculate our forces and our resistances for our walls? Our retaining wall design then generally generates structural forces. Therefore we need structural resistances, so looking at the concrete, reinforcing, steel strengths, and we then have to bring that together in terms of documentation, drawings, specifications, schedules of quantities. The wall then will be built on site, and there needs to be a suitable level of construction control, making sure the conditions on site actually match what we've modelled, what we're anticipating, and that it's been built to the proper standards. And this needs to sit within an envelope of quality control, so checking on our systems, whether they're hand calculations, whether it's advanced computer programs, and the QA of our documentation. All needs to have an overlay of quality, and this all then needs to sit in an envelope of a codified approach, so in accordance with standards and guidelines. So no matter what we do, no matter how fancy we get, we have to achieve all these things with our retaining wall design. So the second part, retaining wall design in a digital age. So the first part is the good old rubbish in, rubbish out. Again, no matter how complex we get with these systems, if we don't get our fundamentals right, those things I've talked about on that previous slide, then we're not going to get the right answers of our retaining wall design. And as we get more and more complex with our design approaches, there's a higher risk that we will miss the key parameters or the key inputs. So with the other part of it is whenever we're doing additional scripting or programming as part of it, there's also additional design checks we have to have on those pieces of automation or scripting which we're incorporating into our designs. So digital design inputs. So what's currently coming into our design? So the recent AGS journal's got a fantastic episode on digital design and inputs of laser scanning, LiDARs, drone surveys. And these are all new inputs which have significantly changed how we design retaining walls. So at the top there's some laser scanning. So that was a research project from a girl at RMIT University. So the universities are incorporating this type of thing as part of their projects. So it's coming up through the graduates. Site-based tablets for data collection or hazard mapping. We then go into photogrammetry processes, so you can create 3D maps or 3D images with your smartphone. If you take a series of photos, you can then paste them together to get 3D models. We then work in much more complex data environments, so common data environments. So graphical data, non-graphical data, our site investigations, and then all documentation that goes with it. So there's a whole new layer of information which we have to process and bring into our designs. And then there's also a construction control aspect as well. So for instance, that's a log sheet in the bottom corner there from a deep soil mixing rig, which is telling you about the grout processes and the torque speeds. So this information is then available, which we can then start to include that into our digital assessment of construction control and quality of construction control. And then there's our design approaches. So there's various levels of sophistication. I should have actually had a paper and pencil up here because that's also an equally valid design approach we could use. So these things range from a piece of paper and pencil. On the middle right there, there's a typical retaining wall detail. So there's tables, and Austral's got examples of these, where for a given retained height and a given soil conditions, it tells you how many blocks you need or how far your straps need to come back. You then start to move into spreadsheets, which have got added complexities or calculations, but also you've got the risk of someone else making changes to your spreadsheet and not detecting them. We then move through software packages. So Plaxis in the middle there is a very common piece of software. FLAC, 3Deck, which is an absolute monster of a program that you really need to be very specialist to be able to use. And so there's a whole range. And as we choose which design method we're going to be using, we're also confined to that design method. We also take on all the assumptions that are inherent in those programs, be they good or bad, and the complexities in them. These often are also standalone packages. So, right, we need to design a wall, someone goes and does the wall design, and they then produce some output from that. It's not necessarily integrated into the whole design process, so they tend to be slightly standalone. But nowadays we can do a lot more complex modelling than we could 5 or 10 years ago. So, complex geotechnical models in terms of soil hardening models, creeping models. We can model much more complex layouts. And we can look at the forces we're getting through in a lot more detail and identify what our pinch points are. So this modelling is, becoming more and more commonplace, whereas 5 or 10 years ago, it was really quite unique. So our modelling ability has significantly increased. So a bit of a case study then, looking at more complex design methods. So this case study is debris flows and retention. So typically, if you're looking at a debris flow, it might be impacting on an urban area, and therefore you may put in some type of retaining solution to therefore mitigate those risks. So a typical approach might be you identify the hazard from a site walkover, and you have to do that to work out what your risks are. You then might do like a GIS flow simulation, so you're modelling that flow paths moving downhill, and then some type of retention design, a rockfall analysis or some type of pressures on the side of a wall. There's a few different ways you can do this. But technology is moving to a degree now that we can then incorporate more complex dynamic models. So in this case, what they've taken is they've taken historic landslides, and they've then modelled the actual debris flows to try and get accurate parameters for the actual soil mass as it fails down. They've then taken structural models. This is in the same piece of software, LS Dyna. They've then taken some structural models. So they've actually replicated meshes with controlled tests, and they've actually calibrated the results from tests with the actual models to make sure they're modelling the structural behaviour correctly. You then start to combine the two of these together. So you can then combine the debris flow with the actual behaviour of the mesh. And of course, they then calibrate that against test examples. And you can then start to then model this in real life. So you're now suddenly looking at 3D models which you've captured from LiDAR or from other methods. You can then model your actually complex debris soil models, and then you can then look at the forces on the retaining walls and structures. So you're not just relying on some empirical relationship on the impact loading, you're actually doing a proper assessment on what the forces are. And this doesn't have to be landslides. This could be vehicle impact loading. This could be a ship berthing loading. So there's a whole range of significantly more complex tools which are available now in terms of modelling more dynamic behaviours. We're also in a much more mobile status these days. So each of you in your pocket has got a little mini computer in your phone. And so you can get apps which can design your retaining wall. So you're on site and you need to change a pile spacing, all the ground conditions aren't right. So you can just go through and you can run it on your phone. That might be a reinforcing calculation. So there's a lot more computing power available to us on site. And data collection is another example. You're then moving into situations of augmented reality, like on the bottom left there. So you may have a retaining wall design, in this case a pile design, and you can actually be out on site holding up your phone or your tablet, and you can actually be seeing how it looks. And I know they're talking to Michael here tonight, like Austral's looking at that type of technology as well. So it's emerging more and more in the industry as this augmented reality type of assessment and understanding for retaining walls and throughout the industry. So the third part, so machine learning, automation and parametric design. So this is a bit of a deviation away. So I'm going to talk about machine learning for a bit, but I'm not going to go into it too much. It's quite complex. Who here understands machine learning or knows about it? Many people? Okay. So this is my simplistic understanding of machine learning. This is what I always think when people talk to me about it. So I'm going to show this and I'm going to talk a wee bit more about automation and parametric design. So could I just get that video going? So this is a piece of programming work done by DeepMind, which is a branch of Google. And if we get this playing. Yeah. So in summary, this is a piece of programming where they compiled a bit of script to enable an object to move. And they gave it some ability to visualize and see objects, and they then just basically told it to move from A to B. That was it. So the program had some constraints on relationships, and it then started to implement those relationships and slowly start to move itself forward. It found new and better ways of moving. It could then start to detect its environment and understand how it should be approaching different scenarios. And it turns out that that's the most effective way to run. So if we can incorporate pieces of script on behaviours and procedures the machines can then take that to a level which we can't, which we could never model ourselves. So machine learning is the ability of a machine to take pieces of information and to continuously improve that and make it more and more efficient to do it better than we ever could. Yeah, exactly. I love this, it's funny. But what does this mean for us? So I had an example before where I showed a soil mixing log from a deep soil mixing machine. For machine learning, it could take the individual pieces of that data sheet and then interpret what the behaviours are and develop relationships. It might take a whole range of CPT logs and from the tip resistance, the friction resistance and the pore water pressure determine what the geology is. It might then relate what one borehole is saying to another borehole and then I'll forward that now. Go back to the side. So it might then take those individual CPT logs and then assess what a ground profile is. You might then give it some information on what a valley formation looks like or what a hydrological formation looks like. It would then take those individual pieces of CPT logs and then overlay potential hydrological features to actually create valleys. So not just interpolating between points, using other algorithms to actually create more complex profiles. So machine learning, it's a big topic, it's a big area, and I just think of a funny running man. That's my base case whenever I think about machine learning. It's self-programming. But automation, so there's quite a few definitions of automation. So this one is one I like, or chosen as scripts or programs which can interpret and automate the execution of tasks which could alternatively be executed one by human. And so this can be applied to simple spreadsheets or very complex modelling software. So you might have a spreadsheet and you might have a macro which copies a cell from one place to another place. That's a very simple form of automation, or something which looks up cells when you paste it in. So there's lots of options and ways in which you can include this in your work. This example was built by a colleague of mine, Andrew Coy, and it's an Excel-based script, and it gets results from Plaxis. And if you've ever worked with Plaxis a lot, you'll know that actually downloading every single modelling stage and cutting and paste it into a spreadsheet is an absolute nightmare. It's a huge amount of work and very time-consuming. So he's then written a script which then automatically downloads it from Plaxis into a spreadsheet, into a nice, consistent format. So the benefit to this is it reduces manual tasks. So scripting can reduce the time which you're spending on your design, on your more tedious works, and it gets you a more engaged team. You know, people don't like sitting there all day cutting and pasting data. It reduces your errors. You know, you've got a consistent manner of importing the data, and you've also got improved documentation. If you set up your templates well, then you can then reuse them and reuse them. Improved productivity and faster delivery, and that's a win for everyone. It's a win for designers, it's a win for contractors, it's a win for clients. The faster and better we can do these things, everyone's going to be a winner. Parametric design. So again, parametric design's got a few different definitions. The one which I've gone for is where model attributes are interlinked automatically. So when one attribute is changed, the other parameters are adjusted automatically. So you change one thing and another thing changes. And this is more and more common in the industry in terms of bridge structures, you know, where they'll change piles, abutment spacings and the size of the decks. But it's also used in, or can be used in, retaining wall designs. It's been around a long time. So Antonio Gaudi, he from Barcelona fame, he used it as well. So he would, to construct his complex models, or his complex buildings, he'd actually hang them upside down. And he'd get bits of string and he'd attach lead weights to them. And the natural shape of which those pieces of string fell was actually the direction of the forces. But what he'd do is he'd change the length of a piece of string, or he'd change weight of one of the shots. And that would change not just one string, but it would then reflect through the model and change the profile and shape of other strings. Therefore, he was changing one parameter and it was then filtering through the model and changing other parameters. And of course, he'd just take the whole thing, flip it upside down, and that's how he came up with his fantastic architecture. In terms of parametric design now, so this is an example from the Western Program Alliance in Melbourne. And so this is Excel-driven visualizations, and this is used in a kind of a concept planning stage for some bridge abutments for a grade separation. So these images are taken a week apart. You can see there's differences in the deck layouts, the type of wall heights, and this is all driven by Excel. So you could be giving someone some Excel information or some Excel data. They then incorporate that into the model, and straight away you've got a visualization, which is then interrelating it. So it's a very powerful type of tool to be using for sensitivities in your modelling. But it's been around for a while. So this case study here is the none and one in grade separation, which worked on with John Holland. And this was 10 years ago. And again, this was Excel-based information, which was then brought into drawing production. So it enabled flexible design. So the grade separation was 720 metres long with 16 different pile types. But as they did the job, they were still drilling boreholes. We didn't know what the ground conditions were doing. So we could have standard designs, we'd understand what the borehole condition was, and we'd say, right, well, you want a type B retaining wall, or we want to change the horizontal spacing of the walls. And we'd change the horizontal spacing in one area, and that would automatically change the pile depth or the shotcrete thickness. And it would automatically occur within the model from Excel-driven information. This meant that we could have relatively accurate designs in terms of our typical sections, but it could then be easily incorporated into our models. And then our drawings then became relatively automated. So we would change a pile spacing, the pile length might automatically change, and that would actually happen in our model. We'd then push print, and out it would come with the changed pile length. And similarly, there'll be a number down the bottom, which would be the tow RL, and that's calculated based on the existing ground surface. So by having simple calculations or processes in a complex manner, admittedly, you can then significantly advance and accelerate your documentation and your design. So on this project, it was 6 months from award to completion, and it was delivered 3 months ahead of schedule. And that's because as we received information, we had a documentation process and design process which could quickly update our documents and update the design, and that could then feed the construction teams on site. So another example of parametric design. So this was some work done by Rebecca in the Arup office in Sydney, actually. And so this is using two programs, Rhinoceros and Grasshopper. So Rhinoceros is the visualization on the left, and Grasshopper enables you to change parameters, and you can do this with Revit and Dynamo if you're from a more structural background. But what we can do here is we can change simple parameters on the anchors, for instance, the bond length, and that will automatically change in the visualization. So you can see there where you can easily control parameters, and there for your documentation, and you can just go and push print on that page, and you then have a real life change in your retaining wall design. You can then start to incorporate this in other ways. So in this example here, again it's Rhino and Grasshopper, we've now got a solid 3D object. It's a relatively simple rectangular object, but we can make it a bit more complex. So we can change the width, the shape of it, change the angles on it, and change the base. So there's a lot of, it gives a lot of variability in terms of doing sensitivities to designs, and a bit more complex, putting a bit of curves into it. So we can simply change a profile, but then what we can also do is we can then connect it to an internet or a website where we can then start to share it. So in this case, we're sharing it through a website called Flux. This video is slightly historic. Flux no longer exists, but there's other websites such as Speckle, which you can then use for hosting. But you can then share a portal with another person of your company, another office, or it might be another company, or it might be somewhere else around the world. They can then log on to the system, and they can then see the model. You can then be changing the model, and they will then see it automatically change as well. So this presents a whole new level of information sharing. It's a new level of information sharing compared to typical retaining wall designs. Once you've shared that information, it's then possible to export it into other programs. So in this case, we're then going from Grasshopper into Tekla, which then enables a bit more of a structural modelling. So you can then assign concrete parameters to it. So you can then take the shared piece of information and incorporate it into other pieces of software. So it's potentially a whole different workflow. Another case study doing a similar type of thing is creating, or in this case modelling, some tunnels Again, using Grasshopper and Rhino, so this could be modified parametrically. Creating the forms, saving them off, and then we actually export them into Plaxis 3D. So those shapes can then be incorporated in, you can then mesh that up, and you can then start to model it. So you can parametrically change things, and then you can bring them into more and more complex shapes. And of course, that model could have been shared across offices. One of the key things with this is you then need to make sure that you're getting your mesh and your techniques right for actually modelling it. And this is where you're then partially constrained by your software, but I'll talk about that in a bit again. So there's whole new options there in terms of workflows in the digital age. So the final part of my presentation is basically a review on where we're at. And I wouldn't be a geotechnical engineer if I didn't have a quote from Carl Tazagi in my presentation. And so I found this one. It's actually on lab testing, but I found it equally applicable, or perfectly applicable, I think, to digital design. So results depend not on the perfection of the equipment, but on the truth of the proposition. So it's about getting, no matter what we're doing, it's about getting our fundamentals right. What's the purpose of our design? Why are we designing it? And making sure that our inputs are correct. The simpler and cheaper the apparatus, the better it expresses the purpose. And accordingly, one can gain insight into a process being investigated, approving or rejecting, and postulating anew without wasting time and money. So if you're using a simple piece of software or a simple design process, it's much simpler, or it's much easier to understand changes and be clear about what those changes are. If you're using something like that Plaxis 3D model and I try and change something, I might suddenly start to get meshing problems, which is just an inherent thing that can happen in 3D Plaxis models. So then I'm having to change my mesh. And so the complexity of the model is driving me down different paths, and I can't actually see the simplicity of it. Or I might be changing some geotechnical parameters, but because of the complex behaviours, it's not quite so clear what's going on. So costly sensitive instruments belong to a situation where one already has a clear hold of the natural phenomenon and where there is a value in obtaining refined numbers. So just because you can do these fantastic complex models doesn't necessarily mean you're going to get value out of it. Simpler design methodologies may be just as effective. When one begins experiments with costly apparatus, he or she becomes a slave to the apparatus and the experiment. Rather than serving to establish the truthfulness of a valuable idea, it serves merely to establish a fact, but never to establish a law. So every process we take on, every more complex piece of software has got its own assumptions built into the software. So whatever we use, we're taking those on, and the more complex it gets, the more complex our assumptions then become. And then this is a slide which is used in terms of automation, and this is basically how much effort should you put in if you're going to try and save time. So an example would be, if you're doing a task on a weekly basis and you think you can save about 30 minutes of time from that, then it's worth spending 5 days, and that's 5 full-time days of effort. If you're spending more, and this is based on a 5-year period, if you're spending more than 5 days effort doing it, you're better just to do the task in the first place. So just because you can automate these things, just because you can do them, doesn't necessarily make it the most effective way. Sometimes it's simpler just to actually do the tasks. One of the benefits if you set up automation or scripting in an effective manner is you can then reuse it on jobs or on projects, and that's where you get real benefit. And then this is something which has kind of struck me in the industry recently, and I didn't want to particularly talk about just one branch of software because there are lots of branches out there. But one of the things that I noticed was in April 2018, Bentley purchased, with a capital D, Plaxis and Soil Vision. And of course, Bentley's already got a very strong suite of software. So they've got GINT for receiving geotechnical data, Open Roads for modelling geometries, MicroStation for drawing and documentation, and that all sits within a project-wise environment. And they've got lots of other software packages as well. When you start to include something like Soil Vision, which is a Canadian-based company which is very good at modelling subsurface profiles and creating hydrological models, as well as Plaxis, then you start to get a start to finish geotechnical design flow. So you can be out on site, you can take your data, you can record it in GINT, you can then create models, relatively complex models using Soil Vision. You can then consider what your geometries are, what your drivers are for your retaining wall, and you can then potentially incorporate those into Plexus models. Might be 100-metre sections, or it might be 3D models. You then have those in an environment where they're then more compatible with drawing and documentation, and all this sits within a common data format of ProjectWise, or in a common system of ProjectWise, where you can then control your versioning and automatically have models updating. So to me, I thought that was a very interesting change. I had a chat to Erwin Betnick from Plexus, and and they're working on trying to get this workflow integrated. It's going to take a lot of work and it's a lot of effort to kind of get that compatibility. But my perception is, I think more and more, this is where the industry is going, about trying to have integrated solutions and utilising the efficiencies that brings. So then, in summary, we have the ability to readily model more complex situations. However, we should consider the value in doing so. Are we really getting good value with doing these complex 3D models, or can we use simpler approaches? And our models are only as good as our design and inputs. So if we've underestimated our geological model, we've got it wrong, or our geotechnical parameters are wrong, or we're not designing for the right inputs, then our results similarly won't be right. Automation can create productivity benefits for design and documentation. It also reduces the potential for manual errors, but you then need to bring in another level of QA control to make sure that your automation, your scripts are actually doing what you expect they're doing, that they're actually behaving properly. And then parametric design and federated BIM modelling, which Melanie will talk about, can bring significant efficiencies to design process and cost optimisation. And finally, our workflows are becoming increasingly more integrated, and I think this is likely to continue. But we must never lose sight of the engineering principles and quality behind our design, and that's the key part. You can't beat a bit of experience to be looking at things and looking, does this look right? And the practical experience of understanding how these retaining walls work, whether they're simple or complex. Thank you very much.
Thank you, Chris. I'd now like to introduce our second speaker tonight, Melanie Binks. Melanie became an architect in 2012, but in the same year moved over to construction, working for John Holland on the Children's Hospital, where she began her first serious involvement in BIM. She then moved to the stadium a couple of months before Multiplex broke ground on site, and spent 3.5 years managing Multiplex's BIM deliverables and the delayed design package for WA's second state-managed LOD 500 BIM project. She stayed on the project until its completion in December 2017, and is now a design manager on the Korinyip Shopping Centre redevelopment project. Melanie has a keen interest in how technology can improve our efficiency, sustainability, and open doors to new ways of designing and constructing. Please join me in welcoming Melanie.
As Catherine mentioned, I'm not an engineer, so please don't hold that against me. I'll just jump. There we go. I started off doing architecture, but very quickly jumped to the dark side, and have been in construction for the last 5 years, where I feel much more at home. And I do all the geeky things. So I'm really glad that Chris is so knowledgeable about retaining walls and how to design them, and all the brains that goes into that, because I don't know much. I've learnt a lot in the last week about it, but hopefully I can give you some insight into what happens with the technology and the data that's available on the big projects where BIM's mandated or available, and some of the benefits that you can see down the line with it. So I'm going to just give you a quick overview of what I think BIM is, and then touch on a few of the projects in Perth that Multiplex have worked on, and the ones that have had BIM involved. I'm going to talk about the current technology from where I sit, and some of the potential benefits that I can see in the next 5 years or so coming from these technologies and the information that's available to us. So for me, BIM, while some people think of it as a 3D model, I see it more as a series of geometry with data associated with it, and the data is actually the important bit. So you'll have Excel schedules you can pull out of it, CSV data that allows you to transfer information between models and software. You've now got cloud spreadsheets that we're starting to link the data in these models to, and my favourite, which is the API connections between software in the background. On site, we primarily use these BIM models and the data for quantity takeoffs, while there's still a lot of hesitation with the contractual side of these models and the quality checking that goes into them. They are a great tool for really quickly benchmarking QS quantities that we get on jobs when you're tendering, trying to keep track of change management, so fluxes in quantities. Obviously, the 4D construction methodology communication is big for us. We've just finished a 3D animated model based on the architects and the structures models that they've done in the consulting world to give to our tenants, so that they can see when we're building this shopping centre what stages will be open, what stages will be closed, how the build goes up. And for people who aren't used to looking at drawings, it's a really easy way for them to see how the whole thing is going to emerge and how it's going to affect them through the project. And then the guys on site, especially on the job I'm on at the moment, are spending hours in the model, just flying through, trying to figure out how they'd actually construct it, the logistics of it, any technical details that they might be able to notice before it gets to site and improve. So yeah, they're the primary users that a contractor gets from a BIM model. And the first one I'll touch on is the Perth Busport. Quick summary, it was for the Public Transport Authority. Finished construction in 2016, so it was one of the first projects that Multiplex did in Perth that had anything to do with BIM. The site itself was 420 metres long and the busport was about 200 of that. And they estimate by 2031 200 buses per hour going through it. So it's got a fair number of buses to manage in the future. And for those structural guys out there, 22,000 square metres of poured concrete. So the majority of it was underground, retained, all that kind of thing. So I asked the team what was their key takeaway from having this model available and did it benefit them through the construction. And they said one of the most effective parts of it was trying to coordinate the live services that ran through the site. Being in the middle of the CBD, there's a lot of stuff that's existing that goes through the site. One of the key ones was the Telstra optic fibre that needed to obviously stay alive through the whole construction. And they were building diaphragm walls straight past this. So being able to not only design the wall locations through the consultancy period, but also hand that over to the subcontractor and make sure that the survey points were bang on, was much easier when they could actually coordinate it using the model. So that was one of their highlights, I guess. Moving on to the stadium, which was 3.5 years of my life, and Multiplex's first full-blown BIM project. So it was state mandated, which gave us a big stick to make sure that quality went in and we could actually use it throughout construction, knowing that the design quality in QA was actually in the model. So some quick facts: State Government of WA, 2,500 precast concrete piles, and then 7,800 CMCs in the surrounding area to try and improve the ground. It was built on an old rubbish tip, so you can imagine what that's like, and then it's in a wetland area, so the ground stability just wasn't there. The stadium itself will be a 60,000 seat capacity, and the structure has been designed with the provision to add an extra 10,000 if Perth keeps growing the way it is. And the steel structure was phenomenal, so I've got a couple of slides later on to show you about that. On the BIM front, I don't know how many of you will actually understand this, but the federated model was made up of all these other individual models that got built by different companies. All up there was about 105 individual models that went into this federated model. They were done by 36 companies, 24 of those got handed over to subcontractors, and all in all, the compressed export file was 2.5 gigabytes. So the Revit models, Tekla models, all added up to about 200 gigabytes in their native formats, but every week we'd spit out a 2.5 gigabyte Navisworks file. The model itself got used by a variety of different people. We had the client who actually co-engaged PDC, who were our BIM consultants, to upskill, do training so that they could actually use the model. They were made up of 4 different arms. You had the sports guys, strategic project, the local government, and Venues West, all as one big team. Then you had the operator of the stadium that came on about 2 years into the project. And the contractors, we didn't use it as much as I would have liked, but we're getting there and upskilling people as we go. Consultants generally have a really good understanding already of Revit and Navisworks and that kind of thing. Subcontractors, they were hit and miss. Some were really good with it. Generally, your mechanical guys, your steel guys are really familiar with 3D modelling and have that down pat. But there were some other smaller, newer subbies that learnt on the job. And we actually handed over the model to the facilities management guys who will use it for the 25 years coming. And they actually have it as part of their contract to maintain and keep the model updated for the government. So the deliverables weren't just the LOD as-built model, but we actually had commitments to make sure during the design and construction process we were encouraging BIM collaboration and making sure that people were trained and getting the most out of these models. So some of the software we used was the Autodesk suite. 80% of the consultants, I think, used Revit. The main exceptions were structural guys who used Tekla. Dynamo is a great little API that plugs into Revit, and we did some pretty fancy stuff with that. Jira was used for issue tracking, brief compliance, and some of our design changes that came through. Tekla, obviously, by the structural guys, they made some phenomenal models. Aconex was our document control and correspondence system, and Arup was our room data sheet, schedule of accommodation. So just gives you a taste of the software that was used and the information carried across all of those, and we tried where possible to get them connected. One of the big wins that we had on the top right was the steel model. The steel subcontractors that we got on board had a really impressive tracking system. So every single piece of steel had a QR code affixed to it as soon as they started fabrication. That matched the ID in the model, and they would track it through all the different stages. So right from documentation through to fabrication, painting, quality checking before it left, delivery, erection, and then the final sign-off. Everything got scanned on the way through. And they were kind enough to give us their Excel export once a week. And because we had a couple of processes set up that allowed automation for the attaching of this data, we literally pushed a couple of buttons on a Thursday when all the models came in. When we came in Friday morning, the program had consolidated it all into the federated model. It had taken that spreadsheet from the subcontractor, attached it to every single steel member in the model, and we were able to colour it like you can see in the top right there. Green was erected, orange was being fabricated, and blue was still in the documentation process. So normally our progress claims and progress reports, lots of graphs and tables and not very exciting things. So we were able to very quickly and easily display the status of the steel fabrication to management and state government and all that kind of thing. And that actually translated through to the plats that we installed, the piles, and even some of the cores that got erected. So just a really nice, tangible way of communicating progress through the project. In the middle on the left was an example of a project where the timeline was hugely compressed. We had the architects still designing the fit out of this building while the steel fabrication was getting processed, and we had to try and catch wherever possible any slab level changes before the steel fabrication came to site. So that was a shop drawing example of a cage that was obviously supposed to be at a particular height, and while it was going through the fabrication documentation process, the architect had set the slab down a bit more. So normally on 2D drawings that's really hard to pick up unless you're really good at RL spot checking, but in a model, very easy to see. So they did all of their shop drawing reviews directly in the model, commented straight on the model, and I can't remember, I think there was about 4,000 steel shop drawings that got processed in probably about 3 months, 4 months. So it really allowed them to get the steel up and running, which from a contractor's perspective is your critical path. Once your structure's up, you're good to fit out. And then on the bottom right, right towards the end of the project, the piling was one of the really effective ways where, similar to what Chris was saying about the parametric design, they were able to connect the bulk of the design and the modelling parameters to a spreadsheet, and the bulk of the work was done on the spreadsheet. So the precast piles, which aren't the ones shown there, were assemblies of 4 or 6 different precast with a cap at the top, and the engineers were able to do their calculations, tweak in an Excel spreadsheet, push it into the model, and all of the 2,500 piles would update to suit their calculations. So there was no manual placing or anything like that. And the second step to that, which helped us, was it was our obligation to hand a model over to the state, which was exactly as built. And the guys who were installing the piles did the bottom RL, top RL, all in a spreadsheet, and all they had to do was import that to adjust to suit the final install locations. The efficiencies in that are just phenomenal. Previously, you'd had to click on every single one and amend manually. This was just a couple of pushes of a button, all done, and you know the accuracy's there. One of the other complexities of having such a compressed program was we couldn't wait for the structural engineer to finish designing and modelling their steel before we gave it to the subcontractor. We had to do a progressive handover. So the stadium was being built from one side around, meeting up at the other side, and as soon as we possibly could, we gave a chunk of the model, took it off the structural consultants, handed it over to the subcontractors for them to start fabricating, while the structural engineers were continuing designing the rest of the structure. And that just allowed the structural engineers as much time as possible to get the design as close as they could before it went to the subcontractors. And the model allowed us to actually attach ownership to every single piece of steel in the model. So people could filter by, okay, that section is owned by the subcontractor, that section is still in design, and progressively allowed us to chase as we went round. So it was a little bit time consuming, but definitely sped up the program and the overall time. Then down the bottom, you can see some of the laser scanning that we had to do. There were 2 parts to it. The first was as the structure was being built around and then connected on the other side, you can imagine the forces and the pull of the stadium before it got connected on the other side. So we had to make sure that the deflections were in design tolerances, and the scan on the left were to check that the columns were within tolerances, and the scanning, I think, was up to 3 mil accuracy. Sat it over the top of the design model, and we could measure the difference from the design location to the actual installed locations as it was going up. And then on the right were the cleats for the facade. So our steel was done by one subcontractor, facade by a completely different subcontractor in China. We had to make sure that the steel was installed close enough so that when the facade panels arrived from China, they could just be bolted straight on. So the differences in these cleat locations got assessed and fixed where possible prior to the install, the panels coming over, and just streamline that process rather than arriving, trying to get it on, doesn't fit, what do we have to fix? And just, yeah, again, allowed us to speed up the process. Getting onto a little bit more of the efficiencies that you can get from the software and simple spreadsheets. On the top right is one of the really easy things that we set up with Excel spreadsheets. A lot of you may know the pain in trying to highlight revisions and changes on a spreadsheet. From an architect's world, it's the door schedule, the amount of changes that you make, and they generally do it by if they change a cell, they click on it and they highlight it yellow, which allows a lot of room for human error, forgetting to highlight things, forgetting to turn the highlight off next revision. So we set up a system where you could just have the previous revision in one tab, current revision in the second tab, and Excel automatically highlighted anything that was different between the two. So saved them a lot of time, gave us a lot more confidence in picking up all the changes, and we actually, on Up, have that sitting on Google Sheets now so that everyone can see it live all the time. In the bottom left, some of the things where we kind of push the boundaries a bit with Clash. Some of you may know already, Clash detection is great for finding things intersecting in a model that shouldn't be intersecting before it gets to site. but you can actually use it for a bunch of other things. In this scenario, we had a door and security devices around the door that were modelled by two completely different companies. But as a contractor, you need to have someone install those security devices. They need to know what door it's going to. Now, the engineers hadn't typed the door number into each of those devices, so we had no way of pulling out a schedule, knowing what doors they went to. But we were able to do a clearance clash where the software picks a radius around the geometry and detects anything within that zone and brings it back in an Excel spreadsheet with a column for the door and then a column for all of the items within 750 of that door. And that allows us to swap the columns around, take the door number and push it into all of those objects and get our schedule out. So we were also able to use this to attach location information to objects in the model rather than having to click on each one and type it in. You run a clash and by default you get grid references in clash data, so you can just push that straight in. But we also modelled some massing objects to get quadrant and zone information in the model. And again, you just push a button, run a clash, pull out an Excel spreadsheet, push it back in again, and you've got all of those quadrant zone data information attached to the geometry in your model. And the column connections one was an interesting one. We got a variation from the subcontractor on a particular column connection where there was a smaller column on top, larger column below, and the detail changed. And didn't seem like much, but when you multiply that by how many occurrences of these columns there were, it was a decent variation. And we needed a quick way of validating the quantity of these columns. So we were able to do the clearance clash between column type A, column type B, find how many they were with grid references for each. So normally really tedious process looking through drawings, but this was able to be automated and sped up. Now this one is a little bit abstract with the slides, so apologies about that, but I couldn't think of a better way of describing it. We had 13,000 bits of furniture that we had to tag with individual QR codes so that the state government and facilities management team could monitor it after. So we had a Revit model with everything modelled, and we somehow had to incorporate this. We got a few quotes that were stupid expensive processes and proprietary software, but we figured out a way just by using API, which I'm not sure if many of you know, but it's like a kind of a backdoor into software that allows you to use some basic coding to broaden the software tools. And in this scenario, it also allows you to connect two bits of software using these backdoors and an API between them to kind of control each bit of software. So what we were able to do was take all the 13,000 bits of FF&E in the Revit model, using an API, Dynamo in this case, pull it into a Google Sheet, which is live on the cloud. And then from there, there's another API called AppSheet, which is a brilliant little tool that from a Google spreadsheet can create an application on a phone. Now I have no app making experience, figured out how to make a phone app in about 2 weeks using this software. So the guys on site were able to take their phone, find any bit of furniture in any room, scan a code and say, yes, I've tagged that one or I've installed that one. And we even actually had a guy in Sydney who's really good at custom coding, and he made his own API that connected Aconex Field. I don't know if any of you have used it, but it's a defecting tool. You have little QR codes stuck up on each room that gives you a list of defects. But we were able to link that QR code in the room to the equipment list for the room. So they could scan this Aconex code, which is for a completely different purpose, and get a list of all the furniture that was supposed to be in that room and the status of each of those. So it would tell you if something's missing or give them a list of things that they needed to install in the room. So all in all, it cost us about $10 a month extra, which I paid on my credit card because I couldn't be bothered dealing with commercial. And that was AppSheet. The rest were free tools that we already had on the project. And we were able to set up a great system that effectively got 13,000 bits of FF&E installed in about 2 months, right at the end of the job. So the possibilities are endless, but that's just a little example of how you can connect the data using the software that you've got. And like the quote that Chris had, the simpler you can keep it, the more efficient it is. So I'm on Arup Shopping Centre now, which fingers crossed will get moving in the next week or two. But it doesn't actually have any BIM deliverables, although a lot of the consultants are modelling in BIM, so we get the access without the obligations to the client, which is a good mix, I think. It's a project for AMP Capital. There's 12 different stages that we've got to hand over at different times. It's about doubling in size, 5 stories of basement, car parks and shopping centre, and 290 stores on completion. So it's a pretty decent job as far as shopping centres go. But I had a chat to the guys who are on site, and because we've had a slow start to it, they've had the time to learn the software, figure out the model, and are actually starting to use it possibly even more than I saw in the stadium, which is great. But a couple of the examples that we've had so far, we've used it to manage all the surfaces that were designed to go straight through the piling, which, as I'm sure you can imagine, wasn't ideal for us. So wherever possible, they got designed out early, and where it wasn't possible, like this high voltage conduit up there, we are able to really clearly communicate that to the piling subcontractor. This is going through at this exact point, please don't take it out, that kind of thing. And generally, the architectural and structural alignment has been much easier with the 3D models sitting on top of each other. You're able to see an architectural change that hasn't been communicated properly through to the structural engineers. And as I'm sure you've all experienced through design, chasing change is a painful process, but having them sitting directly on top of each other makes it easier. And the structural engineers have actually said the penetration, coordination and documentation has been easier because we've been able to say, okay, here's going to be the line in the sand where the structural guys document all the penetrations and do the calculations that they need to. So all of the design consultants work up until that point. We draw the line, they do all their penetrations, and touch wood, there's not many changes after that. We are milking the cloud collaboration spreadsheets. So it's taken a while to get the job off and running, which means the program's changed numerous times. And we've set it up so that we can actually export an Excel from the program into Google Sheets, and that filters through to a variety of different deliverables tables, scheduling tables, and the dates automatically update anytime we get a new version of the program. So that's sped things up. We've got down the bottom left is a combined consultant deliverables table where everyone can see when the other people are submitting, the status of them, and write any comments and things like that. And it just generally improves the communication. And we've even got design change registers that all of the consultants add information to. And again, it's live, everyone can see it all the time. So, from the site team, some of the benefits they said was being able to gain an understanding of the shear walls in the project because you've got an existing structure. The proximity and extent of these shear walls around this structure was quite difficult to get their heads around with the 2D documentation, but being able to fly around the model, switch things on and off makes it much easier. We've got a lot of steel structure that's existing and new attaching to that existing, all on different angles, and again, they just switch stuff on and off and they're able to get a really good understanding of how they would install that, sequencing, all that kind of thing. They're able to take additional measurements and they understand that they're information only, but it stops them bugging all the consultants with RFIs constantly because they can just go in and measure themselves. They said it's really useful to be able to cut a section through the model and see the composition of different details in sequence with each other. So on drawings you normally have individual sheets. It's hard to see them all at once, but they're able to piece it all together in their heads and figure out the sequencing with the model. And they said one of the other really useful things is the ease at which they can review services and how they are reticulated through the structure, especially when you've got the existing sections of the building, and just being able to interrogate those with the structural design. A couple of examples. We had a northern ramp which they reviewed and decided to change from in situ concrete to steel and bond deck. And rather than spending a whole lot of money on scaffolding, they were able to use that as a path to get things crane lifted in and out. And they said that they used the model to review clearances and heights of the ramp at numerous points and make that swap, knowing confidently that was going to save money, even though they had to pay for a bit of redocumentation and that kind of thing. And the second one is the general review of the logistics of things and how they access certain areas. They're able to highlight ahead of time where there would be excessive scaffolding or struts required throughout the construction and reduce those or improve the design of those where they can before it gets to site. So moving forward, I had a chat to, I don't know if you've got BG&E over here, but that's one of the structural guys, structural consultant firms back in Perth. And they did the piles on the stadium and a few other things. And generally, I've been really impressed at the way that they are forward-thinking in how they put information into the model. And the key things were that they are trying to, wherever possible, use the model as the source of all the information. So they're actually pushing data into the model that may not get used in the model, but for the engineers, having that all in one place and accessible, they find more efficient for the design. And recently they actually engaged steel detailers in-house to help them do the final stages of their model. They said actually reduced their time with RFIs because they were able to incorporate the information that the shop detailers would need and shortcut that system. So one of the nicest things to hear, because I think architects struggle with this, hope there's no architects in the room, but they have a tendency to reduce scope where BIM's involved and just avoid it. But these guys were saying that because as part of a structural engineer, you have to do slab breakups and calculations with that kind of thing, they've actually been able to offer more services simply by making that available to the builder, because slab sequencing for the 4D communication is actually really useful for us. So yeah, it was a bit exciting to see that consultants were finding new ways of offering new services that they can get fees for using this technology. So long story short, another slightly abstract slide, but I think that once the industry starts seeing these models as just a central database of information that you can access, you can push and pull into formula spreadsheets if you're engineers, or procurement spreadsheets if you're a contractor, being able to connect things through these APIs, have the information accessible on your phone, and do the change management, overlays, all that kind of thing. I think that's where we'll really start to see the efficiencies and benefit from each other's information being in the models. So yeah, thank you very much.
Thanks, Melanie. I'd like to ask Chris if you could come up as well. We're going to have a Q&A session now, and I'd ask if you have a question, to please put your hand up and we'll come and grab you with the mic. The mic is so that we can be picked up on the recording as much as anything else for hearing in the room. Who's going to go first? So I'll kick off with one then. Do you have any comments relating to the quality of input information required for digital design? For example, better geotech survey, BIM, etc., being developed prior to commencement of the detailed design period?
Yeah, I think. Sorry. Yeah, I think the quality of the information is a key part. So in terms of geotechnical design, having that information there to make sure that your designs match what the conditions are on site. That doesn't mean that you can't accommodate variations or changes, but you need to have the systems in place. You need to be spending more time on incorporating systems that can handle change or can properly control the data to then be able to distribute it. So you've got to spend a bit more kind of a CapEx kind of component on your designs to then effectively save on the design processes moving forward. But you have to invest at the start.
From my perspective, a lot of people ask, will BIM save you money if you're a consultant? And a lot of people say, no, it takes longer. But in reality, the documentation and the modelling doesn't take longer. But because your QA processes can be automated, I don't know about engineers, but architects don't like it so much because you can actually find their mistakes quicker and easier. You can add filters on your Revit model, you can do conditional formatting in Excel and very, very quickly find mistakes, which means from an architect's point of view, they have to put more effort in to get a better quality of output. It's not that the same processes are taking longer, it's that they've got to do a better, higher level. So it's kind of a win-lose. Your QA processes are quicker and better, but that means you've got more problems to fix. So hopefully as we get more practice at this, we'll end up just generally being a better output and a more quality product.
Melanie, I was interested in your one tangential comment that the BIM is used in the long term, will after construction, taken over by the owner presumably, and used perhaps in maintenance and ongoing use of the project. Is that something that is key to BIM as useful in the future?
Yeah, 100%. I think facilities management is one of the most, or it's got the biggest potential to actually benefit from this kind of thing. But unfortunately, they're one of the industries that is a long way behind technology. You still get a lot of facilities management places with big paper filing systems. So the guys on the stadium who are actually using it for the first year this year are just starting to get an understanding of what they can do with it. I went back a couple of weeks ago to help them write an app for them to track their own FF&E after handover. And we've done a little bit of training on them with Navisworks, and they've just asked for another version of the model that's a bit simpler and only looking at the stuff that they want to use. So I'm hoping in the next couple of years they'll start to see a little bit more what they can do with this information and technology, like the consultants have been doing for 10 years now. And I think once they get a grasp of it, that goes to the owners, and that'll filter back around again once they start to see the benefit long term that they can get from this information.
Who else has a question for us?
Thank you very much for all of that. I still, being a fairly old-fashioned engineer, I love all the way these things are able to help me. I get very scared about them being in the hands of people who are not really yet ready to be helped. I particularly, Chris, think of phone apps for designing retaining walls. Scares the shit out of me. Because they're difficult things to design, and I don't want my mum thinking she can do it because she's on the bus, because she's got her phone with her. I also worry about even the brilliant software that we have, black box technology. How much do we know what that program is actually doing for us? Mobility of people. You've got a new guy, he's coming to work for Arup next week, and he tells you he can use this software. I have never seen with any consultant a process whereby we check whether he can really do what he says he can do. He walks in the door and he's let loose on a bit of software. All the controls around this, I think, are a real challenge, and I'd like to know what you think about it.
Yeah, thanks, Stephen. Right, so the first one, your grandma on the phone on the bus. Yeah, I think the key part is, fundamentally through what you've said, it's having an appreciation of the engineering design, understanding what your objectives are and what the information's coming into it. And so if you don't have that information or you don't have that skill set, then you shouldn't be doing it. So while you can have that app on your phone, I think fundamentally you should know, is this an area which you're experienced or suitable to be doing this type of work or not? And that's our responsibility as professionals to all of us, is to understand our area of competency. So the tools are there. I can see that they can potentially be abused, but I think it comes down to the individual person and understanding their areas of competency and making those judgment calls. In terms of these more complex pieces of software, I'll often do a more simple check just as a verification process. So right now at Melbourne Metro, we're using Plaxis a lot to design our retaining walls. We're also running simulations in Through and Wallop, doing much simpler calculations to check that we're getting similar types of behaviour. And that therefore gives us a level of confidence, and it's a simpler checking mechanism to make sure we're on the right track with our design processes. So I think when you are using these more complex systems, I would strongly encourage using simpler systems to make sure that, or an alternative method, to make sure that your numbers are coming out about right. You have to check everything, but you need to make sure you've got confidence. And I think that then flows through into your final point of someone saying they can then use this software. And that's where you have to have that engineering judgment, the experienced set of eyes to understand, do these numbers make sense? And again, I'd also be encouraging that level of quality and checking throughout the systems and processes. Quite often when I'm working with junior engineers, I'll force them to do hand calculations. Simple as that, because if you can't do that, then you don't necessarily understand the problem, and that's where you become dangerous. So, do some hand calculations first, demonstrate it, and then allow them to move on to a piece of software so they can validate almost those hand calculations. That's it.
Yeah, that's you as a responsible engineer. How do you regulate it?
I'd say chartership will be one viewpoint. Yeah, I think. I think it's working within your area of competency. And I think we should all know what our areas of competency is. I don't design reinforcing steel. I've done calculations before in the past, but I think it's working within your areas of competency.
Sorry, Chris, I'm going to harp on the same thing. I'm more from the sports area and been seeing the same type of issues in stormwater for the last 10 years. People can't do the basics. It's great that you say you're a junior engineer to get to do the haircuts first, but I'm just looking at it from an area I'm not involved in, is that our standards going downhill because of the use of these software programs. Everyone thinks they know what they're doing. We don't know what we're doing. How can we bring that back to make sure that it actually gets done correctly?
Yeah, it's a big issue facing the industry. I was talking to a couple of graduates the other night, and they were saying, what should we be doing? Well, these software should be modern. I said, no, don't do anything. You're at university, do hand calculations, understand the fundamentals. And I think that's what we need to be doing. I was talking to Melbourne University about, I assisted with the lecture series for them, and they were keen to incorporate some of this modelling software. And again, we were like, no, stick to the fundamentals, stick to the approaches and the basics behind it, and that's what we need to get introduced in our graduates and moving forward. I think the only other way you can move forward then is experience. There's the temptation to be moving into the software, but then I think it's where more experienced engineers need to be looking and saying, well, does this make sense? And doing some testing on the models. If we change that excavation depth, what does it actually do to the model? Or if you change a prop, or if you change some parameters or a flow, is it doing the things which I'd expect it to do? I think it's a big challenge for the industry to move forward.
There's a lot of trash in and a lot of trash out.
There is, that's right. And I think it's a fundamentally understanding the purpose of the design and the quality information you've got put in there, and having those quality controls overriding it all, then they're vital.
Do you still do the 3 layers of do you still do the 3 layers of checking, where the guy who does the calculations hands it on to somebody else to check it, and then another guy approves it? I mean, certainly on drawings there's drawn by, approved, as well as checked by, signatures on there. I suspect for important projects it will be there.
That's right, and I like handwritten. I don't accept digital signatures. I prefer to have it printed out and someone sign it with their hand. And if I can actually see it signed down, then I'm more trusting of it. So I refuse to accept digital signatures generally. But that's right. I think smaller projects, 2 levels of checking's okay. But I think on larger projects, or it's a higher risk element of work, then I think three levels is good. You want someone to do the work and have some troubleshooting, someone to check the work, and then I think again you want to be going through someone experienced that can go, right, does this make sense? You know, and ask a couple of questions, well, have you considered this and this?
Melanie, I just have a quick question for you. So I'm just curious, you mentioned that you were getting all your consultants and everyone to give a model like every week. And I'm just curious as to how that would all link back in together, because previously I've done a few, like not big BIM projects or anything, but from the structural side of things, you end up changing things just so that your structural analysis actually works, so you don't get weird offsets with your nodes and your members. And then if you're linking that back into like architectural model, like obviously it's going to show that it's different. So I'm wondering how that actually helps and clarifies anything. Like,
I won't say that I know too much about the node design, but I was talking to one of the guys before I came here to try and get an understanding of the BIM capabilities and the translation between, he was saying it's quite a difficult process to get node design software either into Revit or talking to Revit, which is what most of the other consultants use. But Arup were doing the steel on our job in Tekla, and as far as I'm aware, they did manage to have all the members in exactly the right spot, because we actually took their model in the shop drawing review process and sat it directly on top of the subcontractor's model, and that was what they did their shop drawing with, so there was no fudging or anything like that. Whether they had a model on the side that they did those fudges for to get their calculations working, I'm not sure. But yeah, it was our expectations from all of the design consultants that what they submitted to us was geometry in the right positions, sizes, as per the design to coordinate with everyone else. So a lot of the services that had to be reticulated around those steel members from a very early period, we needed to do the penetration calculations, designs, details, all that kind of thing. So it wouldn't have worked if there was any fudging positions. So yeah, whether or not they did it, I'm not sure. I don't know if you have any idea.
Not personally,
Nope,
no.
that's all right. But yeah, I know the architects do have design models that sit off on the side, and they transfer bits and pieces back and forward to test things, explore things. When it gets to a point that they're happy with it, it goes into the construction model. So maybe they had a similar system, I'm not sure.
Any more questions? Oh, sorry.
Just a quick one. What do you say was your most challenging or most interesting project so far?
Okay. I've already talked about the stadium a lot.
My most challenging or interesting project so far, right now I'd go for Melbourne Metro because it's also the freshest in my head. And I guess also from a digital perspective, so we're doing things where we're trying to model things in quite a complex manner in terms of multiple walls, and that's therefore giving us issues with stability of our modelling, and we've had to spend a lot of the time. You know, we've gone down this path of trying to model everything in some level of detail, and that's created a lot of work for us to try and get those models actually stable and actually give them reliable results. So again, we've chosen a complex method, and we've got all the issues that come with that. The stakeholder relations are very complex, and the timing's very complex. And again, to try and accelerate some of those things, I'm looking at ground movements, and so we're doing, like I showed in one of those slides, we're creating tunnels in 3D and putting it into 3D Plaxis and coming up with ground movements from that. So it's not a detailed model, it's not modelling all the structural components, but that enables us to do relatively reliable assessments on ground movements in a relatively effective and a fast approach manner. So yeah, so there's definite efficiencies there from incorporating digital design to make it a lot more manageable from a documentation process.
For me, it'd be the stadium. I'm quite young in my career, so I don't have many under my belt yet, but I think I probably peaked early with that one. That was a hugely compressed timeline, and having to deal with the design progressing while you're trying to build it and all the complexities that entails was phenomenal. And it was obviously a high, or the media concentrated quite heavily on the job because everyone loves stadiums, and after the Children's Hospital in Perth, which I don't know if any of you guys have heard about, but that was the government's first BIM job. Didn't quite go so well, not because of BIM, just it was a painful project. The stadium was their follow-up job that they really wanted to get done on time, and I know Multiplex just wanted it finished on time. So yeah, just the speed of the construction and the design of that project for me was terribly complex, and I think I learnt more in that 3 years than I did my entire architectural degree plus high school years. So yeah, that's easily my most complex to date.
Chris and Melanie, thanks for the presentation. Question for Melanie, did you have to swap between Excel and Google Sheets, and did you have any challenges doing that? And how did you overcome them?
Bit of both. So depending on what the Google Sheets were used for, we had Dynamo set up linking directly from Revit into Google Sheets, so there was no Excel conduit there. But for other inputs for Google Sheets, we would receive an Excel spreadsheet from a subcontractor or something like that. And one of the solid workflows that I developed was to have a Google Sheet where you could import and overwrite directly from the Excel. So there was no other formatting in that Google Sheet. But because Google Sheets allow you to pull the information from Google Sheet A into Google Sheet B, I could have that iterative import process happening over here, bringing in the most recent Excel, and the information would consistently come over in the same manner into my working Google Sheet. So you can do the same with CSV or whatever you want, but it is much more efficient if you can get some API connecting directly into Google Sheets. And with Dynamo, for example, you can even do that live in the model. I'm not sure that's super beneficial at this time, but even just pushing the button at any point while you're designing, pulling it straight from a model, straight into a Google Sheet that everyone can see is really, yeah, it improves the collaboration, I think.
We're going to call it quits on Q&A there. Sorry, just because we got started a little late, we're shortening the time. I'd like to welcome Michael from Austral Masonry, who's going to be our speakers tonight.
Ladies and gentlemen, thank you for joining us tonight, and thank you to Chris and to Melanie. Chris for the second time, so thank you for coming back. You're glad for punishment. We very much appreciate Engineers Australia as well for organising this series, and thank you for all of you for coming out. Look, the festivities for tonight are not finished. We've got drinks available. You're more than welcome to stick around, have a chat with our speakers as well, and obviously our representatives from Austral Masonry as well. But again, look, thank you very much. Thank you for coming out, and have a great night.